nonlinear materials. So for nonlinear materials, I think it's pretty clear where we actually need to use it, right? When your material is behaving in the plastic region, or you expect deformation in the plastic region, okay, then you definitely need to use nonlinear materials. Okay, so here's a list of the material cards that we have. Non-linear materials is actually ductile plastic, especially is under here, Mat S1. And we will also be talking about Mat HE. So if you're dealing with hyperplastic materials, rubbers, then definitely need to use Mat HE here. Okay. Okay, so okay, so I don't need to go through this theory here. When it's plastic, when it's a plastic, I guess you guys are pretty familiar. And also the equation here. Let me see. Okay, so let me just explain a bit on this because this has to deal with when we define the cards for the Mat S1. Okay, so for Mat S1, we actually have the option later on. You see that we have the option to define our curve, whether it's using total strain or using the plastic strain. So the example that we saw earlier is actually defining the curve in the plastic region. Okay, but there's option to define your full stress strain curve also. Okay, so that's the total strain. So just need to be aware of that when we apply, when we set up our material later on. Okay. Large strain is available in Optistruct by default, so there's no need to turn them on. Okay. Large strain when your plastic strain has achieved 5 to 10% plastic region, right? So then you need to actually turn on the large plastic strain. But we already have it in our elements by default, so you don't need to turn it on purposely. Okay. Theory part, I won't go too deep on this. You guys are familiar. Right. So this is just to explain the large strain and so small strain. Okay. Consider this model here where we apply the load and then the second load case we remove the load and then it springs back to the original position, right? So when it's loaded and unloaded, if you're using the small strain formulation, you see something like this. But if we use the large strain, this is again by default already on. You don't need to turn this. Okay, so you see that our solution will be more accurate in capturing the large strain displacement here. Okay. So yeah, this is to show you that there's a difference when we use small strain versus large strain formulation. But rest assured that we already considered this already. Okay, so this is automatically turned on in Optistruct when it's needed. You don't need to purposely set up any cards for that. Right. Strain hardening, we have a few strain hardening available in our material card. You can see that you can choose any of that from our defaults. Okay, so by default, it's just going to be isotropic hardening, but if you have a different hardening, then you can also use it. This is only used if you do not have the stress strain curve. If you already have the stress strain curve, then you don't need to define the hardening model to be used. Otherwise, you can use any of the hardening models here to specify your material. Okay, if you don't have the stress strain curve to define this region here, then you can use any of this. Right. Yep. So that's the hardening rule and also the hardening slope. So that defines the plastic region. But if you already have the stress strain curve, then you actually don't need both of these. Okay, you directly just put in your table here, TID. Okay, so directly put your table here for the stress strain curve. Let me see what else. Yeah, I think I'll walk you through from the HyperWorks GUI later on. Okay, but remember we are using this mat S1. This John Cook here is similar to the John Cook in Radios, right? So yeah, this is new. If you're using let's say John Cook in Radios, you want to use it here as well, you can use this card to set up. Okay, it's basically just a option to turn on under mat S1. Right. Right. So there are a few hardening rules that we can set for the plastic region here. Okay. And then we also need to define the slope. So this is a slope for that. H value here. Let me turn on this. So the H value here defines this slope here. Okay. So we will require that if you do not have the table. If you don't have table, we require the slope and also the hardening rule to use. Okay. Limit 1 here is the yield stress. So basically this is the point that you need to put it under limit 1. Okay. So yep, it's clear. Otherwise, you will just use a TID, table ID, to define the stress strain curve. Okay, for stress strain curve, again, you need to define what's your data type. Is it a total strain or is it a plastic strain? Total strain means that your X means your stress strain they define in the table. XY has to be 0, 0. Okay. Of course, for plastic strain, it starts from the yield point. So yield point, your stress will have certain values. Your strain might be 0. Okay, but your yield point may be your yield stress. Okay, so this is the first point of your stress strain data. Okay, so if you're using total strain, make sure your data here is 0, 0. If you're using plastic strain, make sure data here has some value for the stress. Right. Yeah, so basically this is it. I can't remember what is being used in Radios. I think by default is the total, if I'm not mistaken. Okay, so if you directly convert Radios material into, let's say your stress strain data in Radios, you want to convert it into Optistruct, you just make sure whether you're using total strain or plastic strain. You just define it under the type strain here. Okay, type strain needs to be either 0 or 1. By default is 0. By default it's total strain, so your stress strain data is to start from 0, 0. Okay. If it's not, then you need to define it. Your type strain here equals to 1, and then your stress strain data will start from your yield stress. Okay. All right. So this is the table that's going to define your stress strain data. Table S1. Okay. You see here there's an option for flat. Okay, so flat equals to 0, flat equals to 1. Basically here, because your stress strain might just capture up to a certain point, if your strain exceeds that strain data that you have in your curve, let's say this is your curve and you only have strain up to, let's say, strain n here. Okay. Sorry. Strain. Okay. So let's say you have only data up to strain n, but now your strain has exceeded. Now you have exceeded strain n plus 1. Okay. But there's no data for strain n plus 1. So if you are using flat, okay, so flat here means that this will just flatten the curve. So after, I mean, a good example for this. Let me just redraw here like this. Okay, so let's say now this is strain n. Now you're required to find what's the stress level when strain is has exceeded your data in your curve. Okay, so if you put flat equals to 1, that means after this point we'll just flatten the curve here, and probably we'll get this is actually strain n plus 1. Okay, but if you use the default, which is flat equals to 0, we're actually going to extrapolate this curve. Okay, so then your stress reported will be higher, right? So the stress reported will be higher if you use flat equals to 0, higher or lower, okay? So because it's extrapolation, right? But if you're using flat equals to 1, then it's just going to be the same as when your strain is equals to this maximum strain here. Okay, so just take note of that. What kind of data that you will get if your strain exceeded if the strain in the model is exceeding the strain in your material data, right? Okay, so we support both small and large displacement with the MAT S1. Okay, so it doesn't always have to be large displacement, only can use MAT S1. Even small displacement, you can use MAT S1. Right. What else is important here? Let me see. Of course, if you need large displacement, you need to turn on param large displacement here. We'll see this later on in the non-linear geometry as well. There are two ways to turn on. One is either use the NL palm bracket large displacement or set a param here. So let me just quickly show you from here. Here there's a NL palm card that's being set up. If you want to use it with large displacement, you can define it under here. Okay, so this is the subcase. Under subcase, if you define your NL palm, instead of putting it here, oops, let me just. So instead of putting it in NL palm here, I put it under the NL palm bracket large displacement. So this will turn on large displacement also, right? So if you put my NL palm card under here, this will turn on my large displacement, right? The other way to turn on large displacement is to set up a param card. So let me see, param. Yeah, so the other way is to set up from here. Param, large displacement, you just turn it on to 1. Okay, so this will also turn on large displacement. Right, so in this model here earlier, it was set up here has a large displacement equals to 1. So that's why here in the step here, we define it as NL palm under the normal NL palm here. Okay, you didn't use this NL palm bracket large displacement. Okay, so two ways to turn on large displacement. Right. Always turn on. Right. This large strain solution is always turned on when our plastic strain exceeds the small strain deformation theory. So when the strain that is plastic strain in your model is exceeding 5 to 10%, then we will turn on large strain solution automatically. Okay, so don't worry about that, right? When we report the results, plasticity results, you can actually get all these strain here. You can get total strain, plastic strain, and also elastic strain, right? So you can look from just from the hyperview drop down. You can choose the strain that you want to look at later on. Okay. We will also report this equivalent plastic strain. Okay, so yeah, just take note that equivalent plastic strain is calculated using this formulation here. Okay, so normally especially those abacus users, right? They will normally use equivalent plastic strain. So that's why we have this result here that is also printed out if they want to do a comparison or if they're doing any benchmarking with abacus results. So that's it's calculated at integration point and then average over the volume, the entire element volume. So some of them use this to look at the plastic strain results rather than looking at this total strain here. Okay, so yeah, you can look at both and see which one is more accurate comparing to your testing. Okay. Here are some strain results that we can actually output not just at the corner, but we can also output at integration points. So by default, it's going to output at the element, right? But if you want corner results, if you want an integration point results, then you can turn on these specific cards here. Okay. One general question is, should I always use the true stress strain curve or engineering stress strain curve when I put in my stress strain curve for my Mat S1, right? Where small deformations are concerned, there's actually no difference, not much difference. Okay, but for large plastic strain, then it's better to use the true stress strain curve. Okay, so true stress strain curve is better when you are dealing with large issues. So in general rule, just use the true stress strain curve, okay, and put it in the Mat S1, right? So that's the if all these words here, the rule that you need to remember is just this one: use the true stress strain curve, right? When you're defining the table for Mat S1, okay. So here we have a small exercise to compare small strain and also large strain, right? Of course, if you run with small strain, it definitely won't capture the curve behavior correctly. So the steps are the same. I'll just demonstrate how to set up, especially Mat S1, in using this exercise 2B, which is actually for large strain, right? So you will see that we will actually import a material table inside into HyperWorks to generate or to create that Mat S1 card, okay? And yeah, then set up the rest for the analysis, okay? So this is what we should get. The blue curve that you see is actually from a material testing data, right? So that's the raw data. And then the red curve is what we get from Optistruct. Okay, so we're trying to match the testing material. Okay, so just bear with me a few minutes while I set this up. I know it's close to 12, but I hope you guys can just spare a few minutes to look at this setup here. Right. So I will load the model in. Large strain, okay. Okay. So let's see, the material is there's only Mat 1, right? There's no nonlinear material, so we need to set up for that. Property wise, SP last, but there's no property for this main material as well. Okay, so we need to create a P solid for that, and then define the material there. Okay, so let's just do that first. Let's just create a P solid. P solid, right? Just P solid. Material wise, I can just assign it first to use this one. Okay, because Mat S1 is actually defined underneath. All right, so let me check on the sub case. Oops, there's no sub case here as well. Let me. Oh, we need to create the boundary conditions. Okay. Right, so for boundary conditions, I'll just refer back to the manual so that I will get the same result that is being presented in the slides. So let me just go back to the manual. You can also open up the manual. Then follow the steps in the manual. So I'll just go to 2B. Let me see where are the loads to apply. Let me see. Okay, I have my widgets already. Okay. Right, so this is where I'm going to pull it. The other side is where I'm going to clamp it. Okay. Right, so let me just clamp this part first. So when I clamp this, I'm not going to clamp the entire thing. I'll just let me hide some of these elements first. All right. So I will create a SPC. All right. So just top the top and bottom layer, and just log 1, 2, 3. All right. Okay. So that's the SPC. Make sure it has just created that. Okay. I'll rename this to SPC. All right. And on the other end, here's where I'm going to apply my loading. Okay, so I'm going to apply my loading in the middle here, which will also require an SPC. Okay, if I'm using an SPCD, I need to define an SPC at the point of location, at the point of application. So I'm going to apply the SPCD here, which is the enforced displacement. So I need to define an SPC there as well, right? So SPC, yep, create that. So this one SPC, and I would now create. I will just ungroup this. Create another card. Okay, so just a dummy card first. And then change my card image later to SPCD. Oh, sorry, SPCD ungroup, right? So then I create another constraint, which is called SPCD type now. And I'm going to pull in the X direction. Okay, X direction. Let me see how much. 20. Okay, so it's going to be put in the X direction for 20 mm. So just bring 20 here, click on the point. Whoops. Let me create again, click on the point and create. Okay. So now this is the SPCD. Enforced displacement on this point is going to pull in the X direction for 20 mm. Then there's a SPCD for the clamping side, and SPCD, the enforced displacement need to sit on the SPC also. So that's why we define the SPC here as well. Okay. Right. So that's that. Loading is there. Any question on loading? Test attention test. Hobby is there. Right. So for the material side, now let's create that mat S1. Just need to check on this. We're using table, so we need to read in a curve first. Okay, so for the easiest way to read in is to use the utility tab, and you look at this table create here. Okay, so just click on that table create, and we're going to import a table in from the CSV file, and we're going to create a table S1. Right, but before that, let me just look at the table first, see what type it is. Okay, plasticity, right? So this is table we're gonna read in. It's actually starting from 306, right? So it's plastic strain. It doesn't start from the total strain. So plastic strain curve, and I'll read this in. So just from the table here, import table S1 X. Then we put in the file here, right? So let's just search for the file. CSV. Okay, this is the plasticity. Create a new table. Just call this, no, stress strain. Okay, apply. So it's created. You see it under the curve here. Okay. So you see this is the stress strain curve that we have read in. Okay. So yield is 306. We can update that in our mat S1 here. Okay. So just check mat S1 to enable it. Table TID will be using this stress strain curve. Right. Type just leave as by default it's going to be NL last, so you don't need to do this one. Okay, so by default, yeah, default is plastic, which is elasto plastic material. So we're just going to use the plastic here. Okay. H is the hardening hardening slope, so we don't need this, right? Because we already defined the stress strain curve. Even the U function we don't need. Hardening type we also don't need. We can put in our, this is limit one, which is the U stress, which was 306, and type strain, because we are using the plastic stress strain, so we need to define it here as one. It's not the total. Okay, what if you put it here as 0, or you didn't define this as 1? By default is 0. Okay, but if you put in a stress strain curve that is not 0, 0, here is 0, the first point is 0, and then 306, right? 0 and then 306. If you put it as 0, you will inform an error. Okay, so you will output an error. So yeah, make sure it's 1. And basically that's it. So you have set up the non-linear material. Okay. Remember, just use the utility table create to read in your stress strain curve, and then define it under mat S1 here. All right. So, all right. So this one is done. Set grid measure. You see where's this grid here. So it. Okay. All right. So let me number this first. So that I know which point to output the results later on, or look at the results later on. Okay, so I renumber the node here to 11. All right. So there's node 11, which I'm going to look for the resource later on. Okay. Just make sure our outputs are done. Let me just do a global output request. Okay. Since I'm gonna track the force versus displacement, I will need displacement. I will need force. So force here is actually the reaction force, which is actually the SPCF here. Okay. Yep. Because there are a lot of SPC, so maybe I just want to output for. Let me create that set first. I'm just going to put that grid number 11 there. So that I need output for that. Because there are a lot of SPC, later on I need to search for the SPC. So I'm just going to look at the reaction force of here when I've pulled this one. Okay. Think we okay. Never mind. I have to skip this. We just look at all of them later. I know that if I need, I just go to N11. And yeah, basically that's it. So make sure the SPC force is output for all. Displacement is output for all. You even look at stress and strain as well. Stress is by default on, but you can just turn on here, stress and strain. And yeah, I guess that's all. So those are the outputs that we need. Double check on the subcase. It's not created yet, so we need a subcase. Create load step. Right, so just rename this first. Change this to NL stat, non-linear static. SPC is already there. Okay. Load is your SPCD. Okay. Oh, we need NL pump. So create a NL pump card for all non-linear. We need NL pump. Okay. Initial time set, let's just do 0.1, so you can go up to 10% in the first step. Next, we would need NL out as well. Oops, NL out. Okay. This is to govern the output. So let's just do number of time increment. Let's just say 10. In terms of if there's any non-convergence, it will output that step as well. All right. And now adapt is optional. I probably don't need any static stabilize here. What else do I need? I think that's all. So put in your NL pump. This is large displacement. So if you do not want to create a param large displacement, you can directly use this NL pump large displacement here. Okay. So just do NL pump and then NL out. Okay. I also like to use a monitor to monitor my run. So if you look at the monitor file, let me see if I can pull up a monitor file. Right, so previously, like all this monitor file here, it will actually monitor a grid. Okay, you see the grids here are pretty random. If you want to just track a particular grid, you can specify the grid here. Okay, so it's using this monitor if you scroll down under your subcase, there's this monitor here. Just turn it on, and you can specify which grid to look at. So I'll just look at grid 11 because this is the grid that is being pulled, right? So I'll just look at grid 11. How you progress over the entire simulation. Okay, so I'm just going to track direction 1, which is the X direction, right? So that is more for monitoring purposes. It wouldn't affect the run. Okay, so large displacement, yep, that's all. So I'll just output now. Double check on my material. Yeah, so I need to define it as P solid. Material mat1. Okay, even though it's called mat1, let me just rename this. It's a bit confusing. So I just call steel. This steel is actually mat1, but it also has the mat S1 defined as well. Okay. Right, so let's output this one. I should save it under here. Yeah. Okay. Of course, you can also run directly from here, no problem. Right, but I prefer always to output because I can double check when I look at this. Okay, so just double check. Here we have the non-linear stat on, monitor is on, SPC load, right? So that's good. Now we can run this file. Any question on the setup? If you're lost, you can look through this video again, or you can also follow the steps in the manual. Okay. Load 2. Oh wait, I haven't defined load 2 yet. Where's my load step? SPCD. Okay, I created the SPC card. So let me just isolate. Somehow it didn't update that. So I'll make sure this is SPCD. Okay, update, load type to SPCD. Right, so important that your load is always SPCD. Right. Okay, now I can output. Actually, let me just output this. I can actually change from the input deck itself, but since I've done here, I'll just output here. On the last train, this is the file, save. Okay, export. So I'll just close this and close this. Let me rerun it. Okay. So you can follow the steps here. Of course, my step will be different because I might jump here and there. But if you follow the steps here, you also get to set up your run. They requested for element force because they're extracting the element force of the spring. Okay, I'll just directly use the SPC force to plot. Right. So when I plot this, Okay, later when you see the plot, we have some test results here. You see that there's this test result.csv. This is actually not scaled up to what we are to the units that we're using in our FEA run. Okay, so that's why we need to scale this up and also move the both scale up both the x and y to actually get a match with our simulation results. Okay, because it's not scaled up yet. So let's go back. It's still running. Okay, done. Okay, so it's converged. There's no error to that. All right, all the way up to 1.0. So let's look at the results now to compare. I would first open the animation. Okay, H3D, open. All right, so if you look at stress strain, this is the result. Okay. Okay, it's just a simple tension test. Now let's look at the material comparison. Okay, so I'll just open hypergraph and then load in my model. Okay, change this to hypergraph. Right, so first load in my results from H3D. Y-axis is going to be the force. So I'll just use the SPC force of node 11. Let's just use magnitude. Or you can use X, but I'll use magnitude. So that I don't need to use any absolute values later on. Okay, so X direction will be the displacement. I'll say node 11 as well in magnitude as well. So I plot this. So this is my stress strain curve. Sorry, my force versus displacement curve. Right. And let me load in now the result from the tests. Okay, there's test result. There's only column 1 and 2. So 2 is your force, 1 is the displacement. So here is column 1. Okay, column 1, basically your CSV file is just like this. Okay, so there's just column 1 and column 2. Okay, so yep. Column 1 is displacement, y-axis is column 2, which is the force. Okay, plot that. You won't see anything because the scale is not set correctly. Okay, so just use the move button here. Make sure your second curve is being offset correctly. So scale up to 2, and y scale is it's basically just units conversion. So just refer to the values that's set here. You can scale it up. Let me see. To 1000. Okay, so that is the rate curve is the test results. Okay, force versus displacement of the test results. The blue one is from our simulation, right? So you can see that you might think that, oh, it's not actually, it doesn't match very well. Okay, not really, because we only output 10 results. So if we look at here, the time step that we have, you can see that we only have 10 results here. So if you were to increase the outputs for the simulation, you might get a closer match. Okay, so now we only at a few juncture of the curve. So if you want to examine this better, instead of just requesting for 10 outputs in the NL out here, right? NL out, NL out here, you need to request for more outputs. So 100, for example. So I guess in the manual, request for 20. I think it's also not enough. You probably need to request for 100 outputs. Then you only get a better match. Okay. So for me now, 10 outputs, I only get this, right? In the exercise here, it requested for 20 outputs, so you get a closer match. If you output for 100 outputs, then you get a even better match with the test results, right? So yeah, so basically here, this exercise will show you how to output or how to set up a nonlinear material using MAT S1, and then how you can look at the force versus displacement comparison between the simulation and also with testing, right? Hyperelastic material. Okay. So when you're talking about hyperelastic material, you have to deal with large strain, right? So with large strain comes large displacement. So definitely you need to turn on large displacement for this one, or this simulation here, okay? So yeah, needless to explain what is hyperelastic, I guess you guys are clear. It's normally those rubbers and then some of the foams, right? So we have these hyperelastic material models available in Optistruct, okay? And basically, what we're using actually is basically even if you have the test results, okay, for the tension, compression, and then for shear, we will actually convert those test results, those empirical data, to derive constants for all these material models here, right? So depending, you will choose which material model to use, and then we will use your input data, your stress strain curve, to create the constants for these particular models here. Okay, so depending on which one you choose, we'll develop those models. So it's basically a curve fitting to derive those constants, right? Assumptions for hyperelastic material, we are assuming a response in isotropic material, okay? It's a fully reversible deformation, and it's also fully incompressible or nearly incompressible. So keyword here is reversible and incompressible, okay? So the volume does not change except for thermal expansion. Okay, so if you have any large deformation, it doesn't really change the volume of the material. Okay. Right, so these are some of the models that we have in Optistruct implicit. And then for explicit, of course, we have that foam. Okay, so foam is not available in implicit. It's only available for explicit case, right? And we're using the MAT-HE card here. You might ask which material model is the best to use. So we are actually curve fitting following your test data, right? So if you have test data input, but it's only available in the uniaxial direction, means it's just tension or compression, then Aroda-Boy's model is going to give you a good curve fitting, okay? And it's also good for higher strains. You can see here, this is the test data. The star here is the test data, okay? And you see Aroda-Boy's is this dotted pink line here. We managed to capture that pretty good, okay? And for if you're using the other models like Neo-Hooken and also Muni-Rivlin, you can see that it really didn't capture this second stiffening here, okay, for higher strain here. So yeah, if you only have uniaxial data, then probably Aruda Boyce is the best. Okay, Yo here is behaving similar to Aruda Boyce, okay, but there this brown curve here, right? Right. So these are the formulations. Don't have to worry about it. These are the 3 tests that you actually need to perform. Let me just share my screen again. My screen is cut. Okay. Right, so these are the 3 tests that you need to perform to capture that stress strain data and then put it into the MAT-HE for curve fitting, right? So you have the uniaxial test, your biaxial test, and then your planar test, right? And once you have that test, it's actually put inside his table 1, table 2, and table 4 here. Okay, this is for uniaxial, this is for biaxial, and this is for the planar test. Okay. And then if you know the constants, of course, you put in the constants. Otherwise, using the 3 table that you have put in, we actually curve fit and derive all these constants. Okay. So we choose your model here, which model to use. And then, of course, the Poisson ratio and also density. And then you put in your table data, right? Okay, yeah, the table data is important. And yeah, all these constants here are normally derived based on your table data. If you don't have, then if you don't have the curve data, then you definitely need to provide the constants. All right. Yeah. So example of the 3 test data that we have, and this is plotted using the Muni. Okay. So using the Muni-Rivlin model, these are the data that you provide, and then this is the curve fitting that we have done. Okay, so the blue one is the stress strain data that we provided. Then the orange one is actually the curve fitting. Okay, and in each, if MAT-HE is present in your model, we will actually perform this hyperelastic material constants. We will actually plot this out. We will show you what are the constants that is going to be used to represent your material model, your hyperelastic material. Okay, so yeah, all these constants are printed in the out file, right? And because hyperelastic is a large displacement, so we need to turn on. Always remember to turn on your large displacement, whether through the param or whether through the NL pump, right? So we need to turn on large displacement there. Yeah, tips on large displacement. All these are actually supported for large. Sorry, these are supported, but this one it can exist in the model. It won't fail if you turn on large displacement. But then all these elements here are going to be solved with the small displacement formulation. Okay, so we don't really consider large displacement for all these elements here, but all these here are supported, right? Yeah, so this is how do we get accurate model? If let's say you want to perform a curve fitting test, right? To make sure that Optistruct can get the accurate or can model can derive the constants according to your curve data. So you might want to perform with just one element, right? And then perform that, put in your curve and then get the output, right? Yeah, so always use first order to test. And if you have limited test data, right, means that you only have the uniaxial test, you don't have the biaxial test, you don't have the planar test, then some models like the fully polynomial and also the Ogden are going to give you bad it's gonna give you bad curve fitting, so you don't actually get to derive the constants well enough. Okay. So yeah, probably it's better to use reduced polynomial like the Arada-Boys, the Yo, right, to get better curve fit to your curve data, especially if you only have the uniaxial test. So most of the time, what I've seen is that people only have the compression and tension compression data. They don't have the other test data. So it's definitely better to use the Yo Arada-Boys, those reduced polynomial instead of use the full polynomial. Okay. And if you're dealing with large strain, Ogden is accurate and can capture stiffening, right? But of course, also again, it's not meant to be used if limited data is available. Okay, so we cannot properly curve fit that material model, right? So this is an exercise where actually we already give you the constants in this exercise here. So what you need to do is just put in your constants. So if you refer to the manual, you see that we actually provide you the constants already. Let me see, where is it? Yeah, here. Yeah, so you actually we for this one is Mooney, so we just need to define all these constants here. We give you an example of the constants lah. But if let's say you don't have this, then you need to put in table 1, 2, 3. Okay, so the 3 tables refer to the uniaxial, biaxial, and also for the planar test. Right. So let me just show you how to set up. Again, this is also just a non-linear setup, so it's pretty easy to do. Just do new. Let me just read in the file first. Is it a HM file or a FEM file? Okay. Yep. So just read this in. I think everything is set up. Let's just double check. Loads are here. We don't have load step yet. Load collectors only have the load and the force. So we don't have load step and also the other parameters, the NL parm and so on. Material is defined, but it's defined steel for this part. The rubber actually is not defined yet. P solid is a steel material. This is only for this, not for this. Okay, so first off, let's define the material first. So we can just right-click, create mat HE. If you're using older version, then just create any material and then change the cut image here to mat HE. Okay, so I just want to call it rubber. So you choose which model to use. For this example, I'm going to use Mooney. Right, you can use here. It doesn't matter because we already have the constants for Mooney, so it's not curve fitting. So we don't need to, yeah, we don't need to, like, there's a limitation of which curve fitting is better for which data you have, right? So here we don't have to worry about that because we already have the constants. Okay, so no curve fitting is done here. So put in Mooney. Let me see what's the value to use. Okay, so Poisson ratio, of course, this is gonna be high because this is rubber. So you can put 0.495. If you put it higher than 0.495, we will give you an error. You cannot put in more than, you cannot put 0.5. Okay, even though if that's the exactly Poisson ratio, but you have to put it lower. So 0.495 is fine. Some cases you can go higher, like 0.497 and so on. Okay, so I'll go with 0.495. That's the Poisson ratio. And then the constant that we're going to use, okay, 0.12. All right. So if you do not have the constants, then you definitely need to put in your tables. So you need to read in 3 tables. One for the uniaxial data, your tension compression, the other is biaxial, and then the fourth one is the planar. Okay, so you have to, like what we've done earlier, input in the table create, right, using table S1, input 3 curves in, and then define them table 1, table 2, table 4, right? So with this one, it's actually okay. This is already set up for this material here. Now we just need to define a p solid for the rubber properties, right? So you see, this is the seal. It's not defined any material, any properties yet. So I'll just go down to properties, create p solid. Now you see there's a PL solid and then there's a p solid. For rubber, you can use both. Okay, what the difference is, for PL solid, it is specific for rubber material only, hyperelastic materials only, and it doesn't have the coordinate system. So the coordinate system is always fixed at the globe using the global coordinate system rather than a local coordinate system. So that's the only difference. If you look at the difference between them, the cards, here we can define this local coordinate for P solid, but for PL solid, we cannot define that, right? So it's always going to use that global. Yeah, it's always going to calculate the stresses based on the global or the basic coordinate system. So we cannot define cot M for hyperelastic materials. Okay, so that's the only difference. The PL solid just simplifies that, right? It removes that. So you can use either one. You can use a P solid or you can use a PL solid. Okay, so I'm going to use P solid here. If you want to change it, just change this to PL solid if you want. All right. Then you can also put in your materials, which is going to be the matte HE, and that's it. Okay, so you see the difference between PL solid and P solid. You have more options to, yeah, create all this. Okay, but it's not available for matte HE anyway. So if you use either one, it's fine. Okay. Now we can need to define this for the component. Seal, we'll use that rubber property. Okay, and it's going to use that rubber material, which is the Mooney material model that we've defined here. All right. So the force SPC is already defined. All we need next is to, of course, create those cards for NL pump. So this is a good exercise for you to always create that so that you memorize it. We need the NL pump. Okay, that is always needed. What is the initial time step? Then we also need the NL out. Not need, but it's good to have it because it will organize the way we output later on, right? So how many output do we need? For this, let me just show you if I use time. Okay, I need to create a set. Okay, so I can say create a set here, and this is the set. I'll just rename this to time set, and then I put my values here. So how many outputs do I want? Let's say I'll output 10 at 10 time steps. So here I'll output 0.1, 0.2, right? 0.3, 0.4, 0.5, 0.6, 7, 0.8, 0.9, and then the last time step, right? So if you define it this way, you force the simulation to be done, to be carried out at this particular time, and then output at this particular time or load increment. If you don't do this, then you see previously in our examples, you see that our time step may not properly capture exactly at each 0.1 interval. Okay, you see there's a variation there. Okay, Yeah, so if you just use the NL out and you set the NL to be number of intervals and you set 10 intervals, you might probably get something like this. Okay, it's not exactly at particular that particular time. Okay, so to control that, you can use this one here. Okay, this set here, this set, and yep, so it's done. Now we are going to output. Oops. Let's go back to here. Our NL out is going to output at time, at what time, based on this set time here. So the set time is created under the sets. Yeah, this time set here, which we have created earlier. So it's going to output exactly at these times here. Okay. So now out is done. Now I can create the rest NL adapt. Okay. And then if you want, otherwise I'll just go straight to it, straight to creating that load step. Okay. So yep, so load step 1, just change this to NL stat, non-linear static, put in my SPC constraint. Okay, load, I'm going to choose this force here. Hopefully I'm doing this according to the manual because I didn't look at it. Let's just double check. Where is it? Okay, they're using SPC add. Okay, they have two stats. One is loading and the other one is unloading, and they're using SPC add. Okay, so let's just follow that. Instead of using the constraints, they're using this SPC add here. Which I don't have. Wait, let me just double check. Scale load is just scaled up to 3 times. So yeah. Okay, no worries then. I think this is a different model. So we just put in, I'll call this loading. And I'll put in SPC constraints, my force in the load. This is a rubber material, so we need to use large displacement. So go to, make sure you choose the large displacement option here if you do not want to create a param. And then choose my NL out here. Right, so that is set up. Okay. And I'll do another unloading. Okay, so now this is done. If I want to do unloading, let's say I press it. Okay, so these are the force, I think. Okay, so this is the force. This is gonna be, this steel part is gonna push on the rubber. And when this is loading, you push down, and I'll create another step called unloading. Okay, let me do that. I'll duplicate this and I'll call this unloading. Load. Okay. So unload, instead of having the force here, I'm just going to remove the force. Okay, so there's no force now. It's going to unload, but it will treat this as a separate time step. Has a separate load step until I define this continue nonlinear sub. So there is a continue. Let's see. Yep. So here, this one here, continue nonlinear sub case. So this will actually prompt the second step to continue from the first step. So you need to turn this on. And if it's yes, then this will continue from the previous step, which is the step 1. Otherwise, you'll just treat it as a separate run. That means this is your initial model and then there's no load, which doesn't make sense, right? So we need to turn this on so that it continues from after we have loaded it and then release it. Okay, so that's what we want to do here, right? So we need to turn this continue NL sub on. for the second step. Okay, first step we don't need because we don't continue from anywhere, right? Then we can put a output request if you want. You can put in your basic displacement, your stress strain, your SPC force if you want to look at reaction forces. Stress here, strain here, you can look at that. Since actually we have contacts here, but it's already defined in the model. There's actually contacts between the two parts here. Even look at the contact force as well. You can also output contact force con F here. Okay. So I guess that's all. Let's look at NL out. NL out is set. We probably going to turn on the non-convergence set to yes as well. So if there's any convergence issue, we will capture that final time step as well. I'm not going to use the load add here for now. So I'm just going to use the exact loading without any scale up. Let's see if this will give us some results. Okay. So let me see if I've missed anything. This is turned on. Okay, so the request ended out for 10 steps here, so it's okay. But the initial time step here is 0.01. So let's see if we can converge at 0.1. Yep, so I guess that's it. So we can run this now. I will export this as a solver deck. No need. Okay. Right, so it's finished. Now let's run this. Okay, hit run. Any questions on the setup? Contacts. Right, there's no curve fitting that's being done here because we directly put in our constants. Okay, so let me show you an example of the out file where we do a curve fitting. You can see the notepad, right? This is a setup where I only have the uniaxial data. Okay, so it's a tension compression data, and this is a stress strain curve. Okay, so we put in this table 1, which is this which is for uniaxial, and refer it in the MatHE. Right, so you can see I'm using Arruda-Boy's model, and this is my Poisson ratio. So you can go for hyperelastic is normally 0.495. You can go higher, like what I've done here. It is supposed to give you a better curve fitting if you put higher, but sometimes you'll complain that it's highly unstable. Yeah. So if it's higher than 0.495, you will complain that it's highly unstable. So it depends on whether you can get a good curve fitting or not. Okay. So I'm using that, and I put in my table 1 here, tab 1. Okay, so I need to have the uniaxial data, so that's the one that is being referred to. And if you remember, Arruda-Boy's is good if you have only uniaxial data, so that's why I'm using Arruda-Boy's here, right? So when it actually map it, this is the stress strain data that I've provided. So this is from the test, okay, this row here. This is from the test, and this is the curve fitting that is done within Optistruct, okay? And based on that, based on the table data that we input, we actually calculate these two constants here that is required for Arruda-Boy's. Okay, so these two constants are required for the ROWs. We derive them. So you see the constants are fitted and derived. Okay, and then Optistruct internally will do a test to compare the stress strain that is generated from the derived constants against the testing data. Okay, so you can see how close we are to capture the test data here. Okay. Yep, so this is what I meant. There'll be a warning if you use higher than 0.495. Okay. And what it does is, if you're using curve fitting, you will derive the constants, you will check the stress strain comparing to your input, and you will also check for this material stability here, right? This material stability check, you will check for all the tests whether your material input is stable or not. Okay, so as long as you see this is stable for all directions, then it's safe to use. Okay, if not, then you probably need to switch your material model to something else. Maybe ROWs is not good enough. You need to change to other material models. Okay, so this is the material check that we do. If you put in your input table from the testing data. Okay. So just want to share this to you. Right. Of course, for our model now, we don't see it because we directly input the constants. So they just use it as it is. Okay. It's slow now. The increments actually very small. Or maybe because I started with a very large time step. So the initial time step will have effect. Okay, so it will actually determine whether you get a convergence very early on or not. All right. So let's look at we can look at the monitor file. Okay. You can see that the first time step was 0.1 is actually too large. So non-convergence, it cuts back and cut back smaller and cut back smaller. So if you now know that, you will start moving at 0.001. So maybe the next time step that you want to start, if you have tweaked something, you want to rerun again, you probably don't start with 0.1. You start with 0. Like this time step here. Okay, so probably start with 0.001 now. So if the next run, if I want to make sure that the first step is successful, because if a successful first step will help a lot in the convergence. Okay, so you get to converge faster. So probably the next time I run this, I will change this now, the NL pump. Here I probably change it to 0.001. Okay, so this is gonna be this will ensure that the first step will converge, and then it will take it further from there, right? So this is how you can improve the calculation time. Right, so I will just let this run. Probably gonna take a while because the time set's now very small. Okay. In the end, what you get to see is something like this. So slide, you probably see something like this, right? So there'll be no issue here because these are the constants material constants that we have given to them. So you definitely will get converged runs. Okay, so you can try that out. It's better if you have the stress strain data for the 3 tests, which you can input into your model and then test it out and see whether the curve fitting is good to mimic the exact data that you have given to Optistruct. One thing to note is that when you put in your stress strain data format HE, just going to make HE. It is not exactly stress versus strain. It is stretch ratio versus so it's stress versus stress ratio. So a stress ratio, it's just, let me show you from here. See if I have it defined here. Yeah, so your stress strain data that you put in is actually it's not exactly stress versus strain, but stress ratio. So X is stress ratio. So it's engineering stress versus stretch ratio. What is stretch ratio? It's just 1 plus strain. So whatever strain, engineering strain that you have obtained from the test data, you just plus 1. That is your stretch ratio. So you need to convert your data to stretch ratio versus stress versus stretch ratio instead of stress versus strain. So that's the only thing that you need to change from your raw data. Okay. For all the 3 tables here, we will use that stretch ratio.